problem is working a acid equilibrium problem, working backwards from pH. And so in this case, the first thing I want to do is go ahead and write the reaction, the dissociation reaction of HA. And it's just a general, there's no A on the periodic table, but it's just a general symbol for an acid. And so I'm going to dissociate it into H plus and A minus. So therefore, the equilibrium expression is just going to be H plus times A minus concentration divided by HA. And that's going to equal Ka. And then I notice what they're giving me. So what they're giving me is I have a 0.10 molar solution. And they're also telling me that the pH is 2.75. Well, I know that if I know pH, because going back to our little chart, that if I know pH, I can go backwards to the H plus concentration very easily by doing the 10 to the negative pH. So all I'm going to do is say 10 to the negative 2.75, and that's going to give me my H plus concentration. So my H plus concentration, if I work this out, you can leave it if you're not asking for the concentration, but the problem does ask for it. And so I know that it's 0.00178 molarity. So I know that my H plus, I know H plus up here. So H plus, just kind of rewriting it so you can see it a little better. Well, what do I know? I don't have any A minus from another source. And so if I know my H plus, then it's 1-to-1 with A minus. So I also know my A minus is 0.00178. So then I'm given that my HA concentration is 0.1. And so I can very easily plug this in. I know at equilibrium, this is what I'm going to have. I know it's going to be 0.1 minus 0.00178, but it's not enough to make a difference, not enough really significant digit-wise. And so I'm just going to basically do x squared over initial is equal to Ka. Well, where my x is my H concentration and my A minus concentration, the same value. So I'm just going to plug it in. I'm going to square that. I'm going to divide by the initial concentration. And that's going to give me my Ka value. So I'll give you a second. Then to maybe plug it in. You can pause if you don't want to see it right away. But it's 3.16 times 10 to the minus 5. That's my Ka value. So if we look at the top, I've calculated Ka, calculated H plus and my A minus. And so the last thing it's asking for is percent dissociation. Another way I could have asked that is percent ionization. Just means how much is it really breaking apart. Well, if it was a strong acid, I would have 0.1 molar HA, and it would give me 0.1 molar H and 0.1 molar A. It would break up 100%. But this is not a strong acid. Obviously, I've got a Ka of 3.16 times 10 to the minus 5. So it's not going forward that much. So all you do to figure out your percent ionization or your percent dissociation, I'm just going to call it percent dis, it's just equal to the x, which is our H, over initial times 100%. And so all you do is plug it in. So plug and chug. So I'm going to plug in my molarity of my H. I'm going to plug in my 0.1. I'm going to times it by 100. And this also is the 5% rule. As long as this is less than 5%, then I know I can just ignore the fact that this initial minus x doesn't matter. And so it works out to only ionize 1.78%. So that is my percent dissociation or percent ionization. And so we can kind of collect our answers here for percent. We have our concentrations, and we have our Ka value. Everything they asked for in the problem.